Paper 2 from May 22, Timezone 1. We're going to start with oxidation of magnesium. Magnesium is being oxidized to magnesium oxide, and we're going to write the balanced equation for this reaction where magnesium solid. Make sure we acknowledge the state of magnesium, and oxygen in gaseous state to become magnesium oxide. And what is the state of magnesium oxide? It's an ionic compound with high melting point, therefore solid state. Stoichiometry. We're going to start off with one magnesium for which we would only want one oxygen atom, meaning we will be adding only half mole of oxygen. One magnesium, half oxygen, one magnesium oxide. Group 1 and 2 all belong to the S block. S block of the periodic table. Group 13 to 18, they belong to where? P block. The D block refer to the elements between group 2 and 13. Magnesium is in which period? Period 3, and we study the acid-base characters of period 3 oxides. Magnesium is the second element of period 3, starting off with sodium, magnesium, and then aluminium, silicon, phosphorus, sulfur, chloride, and then our noble gas argon. We start off with basic oxides, starting from sodium, magnesium. Aluminium, it's basic, but also at the same time acidic, which we call amphoteric. Then we transit entirely to acidic from phosphorus. We're going to skip silicon because silicon dioxide is a giant covalent macromolecule, therefore does not dissolve in water to form basic or oxide or acidic solution. Phosphorus, sulfur, chloride, chlorine oxides are all going to be acidic. Again, argon does not form an oxide because it's a noble gas. It's unreactive. So aluminium is going to be the only metal out of sodium, magnesium, and aluminium that does not form a basic oxide, but instead amphoteric. Mass of crucible and lid is used where? Well, this is a question where we are going to work out the amount of the reactant in the crucible by taking away the raw mass of crucible and lid from the mass of crucible and lid and the reactant. So we're going to take away 47.372 from the 53.726 value to work out the mass of magnesium, which would equal to the amount of magnesium when divided by the molar mass. What's the molar mass of magnesium? It's going to be 24.31 grams per mole. Do the math and we'll be given 0.2614 mole. When we worked out the mass of magnesium via the simple subtraction, we could consider the absolute uncertainties associated with the mass values. We are using 0.001 grams for the absolute uncertainties, which means, although we're not asked in this question, we could acknowledge how the 6.354 grams mass value has 0.002 grams of absolute uncertainties. And that's going to be important for our next question, where we work out the percentage uncertainty of, this time, mass of magnesium oxide, our product. How do we work out the mass of magnesium product? Well, we are going to take away the mass of crucible and lid. Again, 47.372 away from the 56.941 value that corresponds to mass of crucible, lid, and magnesium oxide, our product. And that's assuming all the magnesium has completely reacted with oxygen. And what's the value? The value is going to be 9.6569 grams. Again, there will be the absolute uncertainties associated, 0.002 grams. Well, in order to convert this absolute uncertainty into percentage uncertainty, what do? We do 0.002 grams over 9.569 grams times 100, which will give us 0.0209. That corresponds to 2%. Sorry, not 2%. Because we've already multiplied by 100, 0.02%. That's relatively low percentage uncertainty. So quite accurate. As I've expected, the magnesium inside the crucible hasn't gone to completion. And therefore, some of the product has been lost, which means that the actual mass of magnesium oxide is not going to equal to the value we have calculated, 9.569. It will be lower than that. And we're going to find the percentage yield by dividing the actual by theoretical value of magnesium oxide produced. The actual value we have, actual mass of magnesium oxide produced is 9.569 grams. That's what we have calculated. But in theory, the mass of magnesium oxide should be the amount of magnesium times the molar mass of magnesium hydroxide, magnesium oxide. Why? Because magnesium will be converted to magnesium oxide in 1:1 molar ratio. That's why stoichiometry is important. We can use this information, 1:1 molar ratio, to work out the theoretical mass of magnesium oxide that should have been produced. Therefore, 0.2614 mole times the magnesium oxide molar mass, which is 2431 plus 16 grams per mole. Do the math and we will be given 10.536 grams. Okay, so we have lost some product, and that specific amount will be 9.569 grams per over 10.536 grams. Percentage yield will equal to that value times 100, which would then equal to 91%. 91% was the percentage yield of our experiment. Now we're going to look at one of the reasons why we haven't achieved 100% yield. And apparently that's because instead of reacting with oxygen, magnesium has reacted with nitrogen to form magnesium nitride. So we haven't lost any magnesium oxide, but instead we have formed magnesium nitride. And this somehow leads to decrease in the mass of product. How? Well, here's the reason why. If you look at the stoichiometry of magnesium with nitrogen, instead of magnesium and oxygen to form magnesium oxide, 1 to 0.5 molar ratio of magnesium to oxygen, we have 3 to 1 molar ratio of magnesium to nitrogen, and that's quite important. Why is that important? Well, because if we have used 0.2614 mole of magnesium, we will have used 0.1307 mole of oxygen to produce 0.2614 mole of magnesium oxide. But if we reacted with nitrogen instead, we would have reacted, wait, let me specify how we've used 0.1307 mole of oxygen. But if we react with nitrogen, we will only be using 0.08. I'm dividing 0.2614 by 3. 871 roughly mole of nitrogen to give 0.2614 0.0871 mole of magnesium nitride. We're only forming that. And if we convert that into mass of magnesium oxide and magnesium nitride formed, let's see how the mass of product differs. 0.2614, we already know, will give 10.536 grams. 10.563 grams of magnesium oxide. We already know that. That's the theoretical yield we would expect. But for 0.0871 mole of magnesium nitride, we would be yielding let's work out the magnesium nitride molar mass. It's going to be, roughly speaking, 24 times 3, that's 3 magnesium, plus 14 times 2, that's 2 nitrogens, which would give, do the quick math, and will give 8.796 grams of magnesium nitride. We have shown how forming magnesium nitride instead of magnesium oxide will give less mass of product. And that's how we explain the yield, the lower yield. But obviously, we've produced a value of 9.569 that's higher than 8.796, which means that magnesium has reacted with a mixture of oxygen and nitrogen. So just to nicely summarize this 1 mark question, it's a small number of marks, but quite a difficult concept. What we need to say is 0.2614 mole of magnesium forms 10.536 grams of magnesium oxide, but only 8.796 grams of magnesium nitride. Then we're going to explain another possibility where magnesium has not reacted with nitrogen, but somehow we've still lost, we haven't lost any product, we haven't reacted with nitrogen, but any other reason for the yield being smaller than expected? Okay, the easiest way to go about answering this question is suspect the purity of our reactant sample. What if the 0.2614 mole of magnesium that we started off with wasn't that amount but lower? What if the magnesium that we used was not pure, was impure, and therefore the actual amount present in (6.354 grams) wasn't actually 0.2614 mole, but lower? Yes, that would explain why there would be less amount of product formed. So we would say that magnesium reacted was impure for the first reason. We could go to the second reason. Being that the oxidation reaction itself was not complete, but incomplete. Incomplete oxidation could be the reason. And what does incomplete oxidation mean? Well, that means that there's still magnesium remaining in the sample. So when we measured the product amount, when we measured the product mass, the mass of crucible, lid, and product after heating wasn't actually mass of crucible, lid, and product, but mass of crucible, lid, product, and magnesium, which would obviously be lower than the expected value. A long question. We're continuing the question 1 with magnesium nitride formed, where we're going to react it with water to form magnesium hydroxide and ammonia. Okay, we're going to produce alkaline magnesium hydroxide and weak base ammonia. Let's start with balancing the stoichiometry. What do we start off with? Well, we're going to match the number of magnesium on the left and right by giving magnesium hydroxide 3 stoichiometry, ammonia 2 ammonia. Then we're going to make sure we have the same number of hydrogen atoms and oxygen. So we've got 9 hydrogens. No, sorry, not 9, but 12. 12 hydrogens and 6 oxygens. That's perfect to give water stoichiometry 6. 1 magnesium nitride, 6 water, 3 magnesium hydroxide, 2 ammonia. They are well balanced. Still with magnesium nitride and ammonia, but this time we're moving on to the topic of oxidation state determination. What's the oxidation state of nitrogen in the 2 compounds? Well, nitrogen is the nonmetal, will be the anion, magnesium nitride. Therefore, it will have the negative oxidation state of -3. In ammonia, it would also be -3 because each hydrogen will be +1. Next up, magnesium nitride and water will be an acid-base reaction. Why? Because nitrogen of magnesium nitride will be gaining protons to become ammonia. Remember, magnesium nitride will be producing ammonium. And where is this ammonium derived from? It's derived from the nitrogen of magnesium nitride gaining protons. Gains protons. And where are these protons given from? They are donated by H2O to become NH3. In this one sentence, we have shown how nitrogen is the Bronsted-Lowry base, while H2O is the Bronsted-Lowry acid. However, it's not a redox equation because there's no change in the oxidation states of nitrogen or magnesium, hydrogen, or oxygen. Let's look at that nitride ion part of magnesium nitride. We are given the mass number of 14, not given, but we know the atomic number to be 7. And we know the anionic charge is 3-. Subatomic particle numbers can be derived from these information, where number of protons equals to number of the atomic number. Neutrons, the mass number take away the number of protons, so 7. Electrons, in nitrogen atom would be equal to the number of protons, 7. But in the anionic state, there will be 3 additional electrons added, as indicated by the 3- charge. We are now given an isotopic anion of nitrogen 15 N3-, as well as 14 N3-. Oh, I've just said the word isotopic relationship. Yes, isotopes are atoms of the same element with the same mass number, with the same atomic number but different mass number. The isotope 15 nitrogen would contain 8 neutrons instead of 7. I have just mentioned that isotopes are atoms of the same element with the same atomic number but different mass number. I could also say isoelectric atoms with different mass number. Yes, the term isoelectric refers to the same electron configuration, and that means same number of protons as well. But we're now comparing not nitride isotopes but nitride ion with magnesium ion. How can they be isoelectric? Well, it's possible because nitrogen will be gaining 3 electrons to achieve full octet in the second main energy level, while magnesium will be losing 2 electrons, losing its third energy level, ending up with second main energy level full octet. But one of them will have a larger ionic radius, and that would be nitrogen. Why does nitride ion, I said nitrogen, apologies, it's nitride ion, because magnesium 2+ ion has greater number of protons. And this means the nuclear charge of magnesium 2+ is higher, is greater than N3- anion, which means the electrostatic attraction between the magnesium ion nucleus and the valence electron is greater. So the ionic size has shrunk. We have talked about subatomic particles, and we're going to use the concept of subatomic particles to explain why atoms are no longer indivisible units. Firstly, presence of subatomic particles. Let's specify what they are. Neutrons, protons, and electrons. We know they are present, which is why we can say we can further divide beyond atomic level. It's a two-marker question. What else can we say? How about we can utilize these subatomic particles to modify the atomic structure. We could add or subtract electrons to ionized atoms. Atoms can be ionized with addition or subtraction of subatomic particle electrons. Okay, we're back to magnesium and its compound magnesium oxide. This time we're going to explain the nature of bonding, magnesium, metallic, oxygen covalent, magnesium oxide, ionic, with the action of valence electrons. What do the valence electrons do in magnesium to produce metallic bonding? They delocalize. They delocalize across the lattice of metal cations, magnesium cations, creating the metallic bonding, which is the electrostatic attraction between the delocalized sea of electrons and the lattice of metal cations. Metallic bond type is created via delocalization of valence electrons across lattice of magnesium 2+ cations. Oxygen covalent bond, double covalent bond, is made by sharing of electron pair or pairs in our case, valence electron pairs. Ionic bond is created by transfer of electrons, valence electrons, from metal to non-metal, magnesium to oxygen, metal to non-metal. Nitrogen will have 7 electrons that will fill the lowest sub-energy level, 1s, according to the Aufbau principle, followed by the 2s. It will be filling the 3 2p orbitals parallel, according to the Hund's rule, where electrons will only occupy empty orbitals first before they have to fill the half-filled orbitals with opposite spin, according to the Pauli exclusion principle. Ammonia can have a Lewis structure as follow, where there's a lone pair on the nitrogen. Equilibrium constant for any reaction, any equilibrium reaction, is product concentration over reactant concentration. In our case of Haber process, it would be NH3 squared over N to the power of 1 and H cubed. Forward reaction favored for lower moles of gas. Lower moles of gases. POE shifts to the product side, meaning concentration of products increase, concentration of reactants decrease, Kc value. A catalyst will not affect the position of equilibrium because it increases the rate of both forward and backward reaction. Not affect POE because increases rate of both forward and backward. Enthalpy change, yes, will affect POE as well. And we will be calculating delta H value using bond enthalpy values. To do that, let's bear in mind how we will need to break nitrogen triple bond, hydrogen single bonds, but 3 of them. This will require energy input, but we will be releasing energy when we form 6 nitrogen to hydrogen single covalents. 6 because 2 molecules of ammonia will have 6 NH covalent bonds. Let's look at data booklet. Nitrogen will have 9, 4, 5, while hydrogen will have 4, 3, 6. Let's annotate that value. 9, 4, 5 plus 4, 3, 6 times 3. This would be the energy required to break the bond, the reactant bonds. We will be minusing the NH bond enthalpies, 391 from the values, because we are inputting energy to break the bond enthalpies of the reactants initially, aren't we? And we'll be releasing energy in the form of negative values when we form new bonds, when we release energy. Do the math and we'll be releasing overall minus 93 kilojoules. So we know this is an exothermic reaction. To work out delta H value from Hess cycle of delta HF, standard enthalpy change of formation values, we have to set up the Hess cycle first. If we set up the Hess cycle, we will have a triad of the following: N2 plus 3H2 turning into 2NH3, delta H would equal to forming N2, forming H2, forming NH3, where we know that formation enthalpy values for nitrogen in its standard state gas would be 0, wouldn't it? The definition of standard enthalpy change of formation is enthalpy change when 1 mole of a substance is produced, is made from its constituent elements in the constituent element standard states. That's nitrogen gas, hydrogen gas, under standard condition. Therefore, producing N2 gaseous, H2 gaseous will have 0 value. But for ammonia, there would be a value, and that's minus 46.2 kilojoules per mole. Hess cycle tells us that delta H is equal to minus 0, that's the delta HF values for N2 and 3Hs. Specifically, we should minus 0 times 3, shouldn't it? Then we're going to add minus 46.2 times 2, meaning delta H value is going to be 92.4 kilojoules per mole with a negative sign. And this value is slightly different to the delta H value calculated from bond enthalpies for one reason. Bond enthalpies are average values from multiple different compounds and therefore inaccurate. Bond enthalpy values are average from many different compounds. And this is an important point, and therefore inaccurate. Delta H values calculated from delta H4F, standard enthalpy change of formations, are more accurate. Ammonia dissolves in water to form ammonium ion and OH minus, hydroxide ion, displayed in this question as H or minus. OH minus, a better way of illustrating the OH minus produced. Well, we have a weak base ammonia becoming conjugate acid, where the conjugate acid ammonium ion can turn back into the base form. So we have conjugate acid-base relationship. We're given pressure, volume, temperature values. We're given pressure, volume, temperature values, and we're supposed to calculate the amount. So we are going to use the equation PV equals nRT to work out the mole value for ammonia. And once we have the mole value for ammonia, we're going to dissolve that in 2 dm cube of water to calculate the concentration value. P is Pascal. It should be Pascal, not kilopascal. So we will have 100,000 Pascal times 900 dm cube. It should be in meter cube, therefore 0.9 meter cube. N, R, 8.31 gas constant joules per Kelvin per mole times temperature 298, no, not 298, 300 Kelvin. Therefore, if we work out the N to be 100,000 times 0.9 over 8.31 over 300, we would do the math, end up with 36.1 mole. That's a lot of ammonia. Let's dissolve that in 2 dm cube of water, meaning that in every dm cube of water, we will have 18.05 mole per dm cube of ammonia concentration. Just in case, let's round up our concentration value to 3 significant figures. Hydroxide ion concentration in ammonia can be calculated if we are given pH value. How? pH value being 9.3, we can tell pOH is 4.7. Sorry. Oh yeah, 4.7. How do we know that? Well, we know pH plus pOH equals to 14 from the ionic product of water. pOH equals 4.7 means OH minus concentration equals to 10 to minus 4.8 mole per dm cube. We still need to calculate this. So if we do the calculation, this would equal to 2.0 times 10 to minus 5 big mole. So if the pH is 9.3, what's the concentration of ammonia in that solution? We will be using the expression Kb equals to NH4 plus concentration times OH minus concentration over NH3 concentration expression. Because we know what Kb value would equal to from the data booklet. The data booklet tells us the Kb value of amine to be 4.75. So let's equalize Kb to be 10 to minus 4.75. Just like this. H plus concentration equals 10 to minus pH. Therefore, Kb value is also equal to 10 to minus pKb. And we also know how the OH minus concentration is 2.0 times 10 to minus 5, as we have worked out in the preceding question, which will also equal to ammonium ion concentration. So we can square 2.0 times 10 to minus 5. Our unknown ammonia concentration value can be calculated as 2 times 10 to minus 5 squared over 10 to minus 4.75, which would equal to 2.24 times 10 to minus 5 big M. Magnesium chloride can be separated into magnesium 2 plus and chloride. Let's read this. The purpose of electrolysis is to separate Mg2 plus from Cl minuses to produce magnesium solid and chlorine gas. We will need to reduce magnesium 2 plus to magnesium solid, and that is indicated by magnesium 2 plus liquid turning into magnesium with addition of electrons solid, where we will see deposits. But if the temperature is right, the state of magnesium may be molten liquid if the temperature is high enough. Magnesium is more reactive than zinc. Yes. How do we know that? Because if we react with acids, the rate of reaction will be faster, and this would be physically observed by more vigorous hydrogen gas bubbling. Faster reaction rate, hydrogen gas bubbling, more vigorous. Now that's one standard experiment, but you could talk about another. We could talk about zinc and magnesium displacement reaction. What if we have magnesium displace zinc 2 plus from its salt solution? Zinc will precipitate while magnesium dissolves as it oxidizes into Mg2 plus and takes place of zinc to form magnesium salt solution. Organic chem, where we have what seems to be a ketone turning into an alcohol, a propanol turning into a 2-methyl propatool. 2-methyl propatool because the functional group alcohol is at carbon 2 position. Now the stem, the carbon skeleton, has 3 carbons, therefore we'll designate propatool and assign the substituent methyl group at carbon 2 position, therefore 2-methyl propatool. In compound B, the strongest force would be hydrogen bonding. Yes, there will also be dipole-dipole London dispersion forces, but we all know hydrogen bonding will contribute the greatest to alcohol's high boiling point. Compound A does not have any hydrogen bonding, which means that compound B will have higher boiling point than compound A. Our alcohol compound B can be prepared via electrophilic addition of water to an alkene, and that alkene would be a propene, but with a methyl, will be 2-methyl propene. Water added to this 2-methyl propene will undergo electrophilic addition to produce our alcohol. Obviously, addition of a non-symmetrical electrophile water into a non-symmetrical alkene will result in the presence of major product as well as the minor product. Our 2-methyl propene monomer can undergo polymerization to form probably a plastic, and the way to show this is how the monomer reacts with itself multiple times so that we create a polymer with a repeating unit, where the repeating unit would be very similar to the monomer, but the double bond will be broken so that we can have extending single bonds from the two carbon atoms that had the initial double bond. Where the monomeric unit would look as such. Compound B, alcohol, is warmed with acidified potassium dichromate. And what is potassium dichromate always used for? It's the oxidizing agent for oxidizing alcohols into aldehydes or ketones. And for aldehydes, further oxidation into carboxylic may also be possible for the right condition, distillation under reflux. However, there's a pitfall here. What's that pitfall? It's only possible for primary and secondary alcohols. Oxidation for tertiary alcohols is not possible in our compound B case. It is a tertiary alcohol, which means that there's no oxidation, which means that there's no change in the color of the oxidizing agent. No change in the usual orange to green color change. No change in color of potassium dichromate. Iodomethane is used to prepare CH3 magnesium, magnesium iodomethane, which can also be converted into methanol. Okay. Yes, a halogenal alkane can be attacked by a hydroxide ion in nucleophilic substitution reaction. In our case of primary halogenal alkane, this will be an SN2. Nucleophilic substitution. Two reactant molecules colliding together must have, firstly, sufficient energy that's greater than the activation energy, as well as the correct geometry or orientation of the collision for successful reaction. Therefore, the requirements for a successful collision would be sufficient energy, specifically greater than the activation energy. Secondly, correct collision geometry. A bit of allusion, a bit of linkage to topic 16, kinetics, Arrhenius factor. Remember, there's the equation, small k, k equals A, big A, exponential minus activation energy over RT. Arrhenius factor accounts for the collision geometry orientation. Polarity of carbon halogen bond is why a nucleophilic attack is possible in the first place. The presence of halogens make the central carbon atom partially positive, therefore prone to attack by nucleophiles. Which means that if the polarity changes, the reactivity of the halogen alkane with nucleophiles will also change. Bond polarity decreases down to group 17 because electronegativity difference between carbon and the halogen decreases. It's not a smiley sign, it's because electronegativity difference between carbon and halogen also decrease.